Hey everybody, welcome to lecture 5.5 on the chain rule for multivariable calculus. This chain rule is very similar to the chain rule you learned in single variable calculus, where you have a composition of functions and you want to compute a derivative of that composition. However, things are much more complicated when your function may have multiple input variables, and each of those input variables could also depend on further variables, and so on and so forth down the line. So what we're going to learn in this video is how to state and use the chain rule for compositions of functions that may involve multiple variables along the way. And we'll also learn a trick for computing implicit differentiation, even on the single variable calculus type equations we had implicit derivatives for, using this new chain rule of a multivariable function. So to get started, here's a motivational example that we've seen before. I just want to return to briefly discuss it without writing anything down. So we had Genteki Corporation that made widgets that sold for a certain price. Right now they're selling them for $100 per unit. And we know that the corporation doesn't produce enough in the marketplace for this type of product that its overall production level would affect the prices for the product. However, when we were discussing this problem in class, we did comment on the fact that if we increase production of the number of widgets by a sufficient amount, then that increase in production should affect the operating cost of the whole operation. So we had the equation for Genteki's profit based off of production and sale of these widgets. That was given by P for profit equals 100 W minus C. And again, 100 W is representing the fact that each widget is sold for $100 per unit, and the cost is subtracted because we subtract the operating cost in dollars. Now, at the time, we had discussed the partial derivative of P with respect to W and said that this indicated that an increase in widgets would result in a $100 increase in profit. However, if we correctly keep track of the fact that an increase in production should affect the cost, even however small that increase or that effect might be, that we need to do a little more work to determine how an increase in widget production would result in a change in the profit. It could be that increasing the number of widgets at the current price point actually results in a high enough cost offset that the profit goes down overall. And how do we take this into account? So this is the main thing that we're going to use today to motivate the discussion of the chain rule. And in particular, if we had, well, P is already written as a function of W and C, our production and cost variables. W is, in some sense, the independent variable that we can choose a value for, and everything else is determined. But cost, on the other hand, the production cost, or rather the operating cost, could be affected by the number of widgets produced, and we'll use W as the sort of the avatar for overall production rate that could affect cost. So C, behind the scenes, could be a function of W, and we need to take that into account when computing rates of change. By the end of the video, you'll have the tools to correctly assess this problem, and I encourage you to come back to this motivating example and examine things further at the end. There's another way to discuss rates of change of multivariable functions when there are layers of functions or compositions of functions involved. And the physicist's way of doing this is by imagining there's some particle that's traveling through space. Let's imagine there's a particle whizzing around in three-dimensional space. This could be the International Space Station, or an asteroid, or just a fly buzzing around the room. And for the purposes of this slide, we'll just pretend that we're only mapping the X and Y coordinates. We're keeping track of the X and Y coordinates just as a two-dimensional coordinate space. But you can do this in higher dimensions. And if we want to track the actual the rates of change, like the velocity and other things about this particle, but we want to really track the journey, the trajectory of this particle through space, we want to visualize this as following some parametric equation or some curve given by X and Y coordinates, each of which depends on a further variable called T. We'll think of T as a time variable. Now, this visualization, excuse me, this visualization is really concrete when you're a physicist or when you're talking about the motion of a particle through space as time varies. But it can also be used as a clever visualization of other compositions of functions. So we'll sort of keep this in mind, that there's a hidden variable behind the scenes, in this case time, that as we tick off seconds for that variable or tick off units for the behind the scenes variable, the input variables for some function will change accordingly. So in this case, X and Y are each variables of the time variable. If we want to measure velocity of a particle, we can look at the vector whose directions or whose coordinates are indicated by the first derivative of each of those coordinate variables, those position coordinates with respect to time. And the velocity vector points in the direction of travel at any instant in time. And as the particle travels through that parametric curve described by this equation involving x and y coordinates, the velocity vector will indicate where it's traveling next at each moment. Here's a visualization. Here's an actual graph using a computer of what's going on. So if the motion of a particle through two-dimensional space is described by this spiral-looking curve in blue, at any point there's some function of x and some function x of t and some other function y of t that together give you the x and y coordinates of a point in the plane. So as we slide t, and you can go click on the interactive version of these slides to move the t bar here. As we slide the t bar around and move forward or backward in time, the particle travels along the curve accordingly. At every given instant, the tangent line to this curve is given by the vector with x prime and y prime in the two components. And that's the velocity vector. That tells you not only how fast you're going by taking the magnitude or length of this vector, but also in what direction the particle is currently traveling at that snapshot in time. If we want to do this in a higher number of variables, we can think of not just tracking our particle in 2 dimensions, but also tracking the particle in 3 dimensions. And if we imagine that the height off of the xy plane is given by some further function f depending on x and y, or in other words, if we have a function f of xy and we look at the graph z equals f of xy, that's this sort of curtain-looking 2-dimensional surface that's in the lighter color here. And we imagine that our trajectory, the path of our particle, our fly buzzing around the room, has to always land on this surface described by the function f. Then what we see here is really a composition of functions. F depends on x and y, those input variables just coming from the position in the coordinate plane down below. And that determines its height. But furthermore, as time ticks off, the x and y coordinates themselves that are inputs for f also depend on a further variable t. So we can think of this as a composition. Here it's written explicitly, f of x of t and y of t. And what's really going on here is that f is a function of t, a single input variable. So it's a single variable function, and we want to know what its rate of change is with respect to changes in the time variable. So that's the setup for the chain rule. And of course, if we have equations for x and y, and we plug them into f, and then we further plug in all of the t variables and get f as a single function, we could just take an ordinary derivative. But that's assuming we have a formula, and in many instances, we may only know partial information about the coordinate variables x and y. So here's the theorem that allows us to perform a lot of calculations in situations like this, and it's called the chain rule. But I want you to keep in mind that this is a multivariable chain rule that's telling you about the rate of change of a multivariable function f of xy, and we'll do higher numbers of variables later, in terms of some input variable t that controls both of the variables x and y. So given that setup, the rate of change df dt is given by either of the following formulas. So the first explicit version we'll use quite a bit is it's a sum of 2 terms. Each one has an x or a y. For the x term, we take the partial of f with respect to x and multiply by the derivative of x with respect to t. And for the second term, we do the same thing with y. The partial of f with respect to y times the derivative of y with respect to t. I'm going to point out a couple of things here, but first of all, the second formula, which is equivalent to this formula, says that we can compute this explicit expression by taking the gradient of f at xy, or just the gradient as a function of xy, and taking the dot product with that velocity vector, x prime of t, y prime of t. X prime of t and y prime of t are just alternative ways of writing these dx dt and dy dt expressions. So these are equivalent formulas. So I want to point a couple things out. First of all, again, this is a rate of change of f, what we think of as the height function off of the xy plane with respect to the time variable. And it sometimes helps to keep track of units as if f is given in some units that depend on x and y, but they're output units and t is in time, then you can write this as a rate of change of the height with respect to time. On the other hand, each of these terms has separate units or is reflecting separate rates of change. So partial f with respect to x is a partial derivative since x depends on two input variables, and likewise for partial f, partial y. Whereas on the other hand, dx dt is the rate of change of a single variable function x of t. Since x only depends on one input variable, this is an ordinary dx dt derivative computation, and likewise for dy dt. So we're going to use this theorem quite a bit. Take a moment to process this. If you like the dot product version of capturing formulas like this, we use the similar thing for the directional derivative, then definitely download this one into your brain and keep in mind that it's a dot product. But I'm mostly going to explicitly write out the chain rule this way because this is how we use it in computations. Here are a few more remarks about the chain rule and what these rates of change are expressing. The first bullet point we already talked about, f is a single variable function because once we plug in all of the x of t and y of t stuff, it only depends on that input variable t at the end of the day. So df dt is the correct notation as this is a single variable derivative. A quick warning, df dt is not the slope of a particular graph. And the reason is that the slope of a graph would be given by rise in the z variable over run in the xy plane. And this is if c is equal to f of xy, by the way. So if we're literally thinking of this as the height off of the xy plane. Whereas df dt, what is this expressing? As we said a moment ago, this is the rise in z, or the change in f, as we change the input variable t. So if we go back a couple of slides and look at the height function here, and we track our trajectory on that height function through this black curve. This is the result of plugging in the t variable into x and y and then calculating its height at any point to get the height on the black curve. The rate of change, or rather the slope against this black curve, is not captured by df dt. Rather, the change in height directly, not as we move around, but if we just took that height as a single output, that thing is changing according to the input variable t, and that's what df dt measures. So it's not quite as visual as slopes that we've been working with before. The chain rule, by the way, looks very similar to our definition of the differential. And if you put dt's everywhere, then it is the same formula, but the proof is actually a little more complicated than just sticking dt's into this formula. So if you already knew that this is the definition of the differential, you wouldn't be able to immediately deduce the chain rule just from this. If you want to see a proof of the chain rule, you can ask me later, or you can look this up and we can discuss outside of the lecture video. So let's do an example to practice with the chain rule. Let's suppose that we have some function p of r and c. Maybe this is the profit, and r is the rate of return, and c is the cost for a particular production of some product, or something more abstract than that. And separately, we have that r is a function of w, and c is also a function of that same w, where w could be the number of widgets produced, for example. And this is exactly unpacking a potential situation that the Jinteki Corporation profit function could experience, where the rate of return is 100 times the number of widgets produced, and the cost is determined by the production level by this slightly more complicated formula than we had before. And let's try to figure out the rate of change of p with respect to w, or in that example, the rate of change of profit, the change in profit, by every one additional widget produced. That's what this rate of change will tell us. So you have the chain rule formula on the previous slide. And if you want to pause now, I just repeated the formula here and all of the pieces that you'll need to calculate the full description of the formula. You can pause the video now and try to work this out for yourself. There's really nothing mysterious going on once we have the chain rule formula. And again, we're not proving it this semester, but it would be a good idea to see a proof of this at some point in your life. So we're going to compute dp dw, and I'm going to continue talking through. So this is your final warning to pause if you don't want to see any of the answer worked out. Using the chain rule, we can express dp dw as two terms, one with each of the input variables for p. And you'll notice that, again, p depends on r and c. So for the r term, we have the partial derivative of p with respect to r times the derivative of r with respect to w. And for the c term, we have the partial of p with respect to c times the derivative of c with respect to w. I'm going to work each of these out symbolically for you now, and then we'll put them all together to get our final formula for dp dw. So first, the partial of p with respect to r. we look at our function here, c is a constant, r is the variable. We take the power rule derivative to get just a single number 1. Likewise, p as a function, or the partial of p with respect to c, r is a constant, and c is the variable, so we'll get a -1 for that term. And depending on how complicated the parent function, here p is playing the role of f from the theorem. Depending on how complicated that formula is, you could get fairly simple partial derivatives out that won't make the final formula look too gross, but you could get more complicated expressions as well. On the other hand, let's do the ordinary single variable derivatives using our individual functions r and c in terms of w. So for r, we see that the derivative in terms of w is just 100. And for c, and again, these are just power rule derivatives at this point, the 3000 is a constant that goes away, and we'll get 70 minus 0.2 w. And finally, I'm going to put all of these things together to get my expression for dp dw. So I'm just reading off of this formula and plugging things in now. dp dr, or partial p partial r was 1, and dr dw was 100. On the other hand, partial p partial c was -1, and dc dw is 70 minus 0.2 times w. So to simplify a little bit, I have 100 minus 70, that's going to give me 30, and plus 0.2 w. So you might have to look back at the classwork where Jinteki Corporation originally appeared, but the question we were asking then was, what can we tell about the profit if we increase production of widgets by 1 unit or 10 units or something like that? And actually, no matter what the increase in widgets is, no matter how many additional units we decide to produce, it's clear that dp dw is positive for every positive increase in w. Or in other words, no matter what the current production level of widgets is, any increase, and as long as it's positive, we're not producing negative widgets, any increase in the number of widgets by any number of units will result in a positive increase in profit. So this is essentially, this widget product that we're selling is a gold mine. Any additional increase in that actual product will result in more profits for the company. Or phrased even a third alternative way, an increase in production is not the profits from increasing production and selling those additional products is not offset by the increase in cost associated to the additional production. So that's a great product, but of course it relied on the fact that the overall market price, the demand for the product wasn't affected by this particular corporation increasing their number of products produced. So that's a special situation, and of course market economics are more complicated than this simple looking function, or these 3 different functions are encoding. So this is our first example, and it's great we had an application so we see the full force of the chain rule at work. Let's see what else we can do. So there are a couple ways we can make things more complicated and see how far we can push our description of the chain rule. So if x and y are our input variables for our function f of x, y again, we could have x and y being multivariable functions themselves. They don't just have to depend on the time variable. And I'm not going to come up with some contrived situation off the top of my head that is as satisfying as the fly that's buzzing around the room according to some trajectory curve. But you can imagine x and y having some sensitive input variables, and each of them emit rates of change with respect to each of those input variables s and t. Those will be partial derivatives now. And we can then ask for the partial derivative of f with respect to each of those original input variables s and t. So there are 2 versions of the chain rule then, one for the partial of f with respect to one variable s, and the other with respect to, sorry, this is the dot product version formula, and then there's another one with t in place of s. So for the partial of f with respect to s, we can write this using the chain rule as the partial of, and this should actually say the partial of f instead of z, but we're thinking of z as equal to f of xy. So the partial of f with respect to x times the partial of x with respect to s, plus the y term, which is the partial of f with respect to y times the partial of y with respect to s. And you can encode this as a dot product as follows, where instead of the velocity vector x prime, y prime, in this case, we're taking rates of change with respect to one of the variables s. So the velocity vector, I'll put it in quotes, but the vector that we can dot the gradient by is the partial derivatives of x and y with respect to s in both cases. So let me talk a little more about this. So there's a version of this where I put t's in place of s's, and I don't have a slide for this. And in the velocity type vector, there will be a partial with respect to t for both these variables x and y. And what this is doing is that it's expressing the possible rates of change of f with respect to the set of original input variables, in this case, s and t. So f is a function that depends, first of all, on x and y, but those separately depend on input variables s and t. So we can view f as a function that depends on, once again, two input variables s and t. And since it's a multivariable function of s and t and no longer a single variable function, it has partial derivatives with respect to those input variables. And we could also ask about the directional derivatives of f with respect to unit directions of change in the st plane. And that's where things get more complicated. But if you keep in mind, this chain rule formula helps you evaluate the partial derivatives in the s direction or in the t direction, then you can use dot product formulas for the directional derivative in terms of s and t, and this chain rule to express the partial derivatives to compute your gradient function. So we can start lumping all these things together, just like you saw in single variable calculus, where chain rule problems can get complicated pretty quickly. It's just a matter of going step by step and layer by layer through the theorem. Another way that we can generalize our original chain rule, rather than allowing more input variables for x and y directly, is we could allow more input variables for f, but keep each of those. Let's say f is a function of 3 variables instead of 2, f of x, y, and z, but keep each of those coordinate variables x, y, and z just functions of a single variable t. So if we have this setup where f is a function of x, y, and z, and each of those is a function of time or some other variable t that's not necessarily time, then the rate of change of f with respect to t is again computed as a sum of terms for x, y, and z separately. The x term looks like partial, or actually the x and y terms are identical to our original chain rule, but we have an additional variable z, so we'll just tack on an additional term, which looks like the partial of f with respect to z times the rate of change of z with respect to t. If you want to write this a little more compactly using vectors and dot products, it's the gradient of this 3 variable function, which we know how to compute from the last lecture, times the velocity vector now in terms of all 3 coordinate functions, x, y, and z. And you could get really crazy and say, what if we have a function f that's a function of x, y, and z, and then each of x, y, and z is a function of multiple input variables? Instead of just s and t, we could add on even more than that. And there will be similar expressions in that case for all of the partial derivatives with respect to all of those initial input variables. This gets quite complicated to compute, but theoretically it's possible. And this is sort of the beauty of this type of mathematics, that even if the answer is hard to come by, there is a path to follow carefully and get to the answer. Here's a situation that we haven't spent too much time discussing, but it's important in physics and really in material science, that if we have a gas, ideal means that we're holding a bunch of other things constant. But if we have a gas, we're not changing too much about it, then the pressure of the gas in an enclosed space is given by the function nRT divided by V, where R is a particular constant depending on the makeup of that gas. N is the number of molecules of the gas, and really N is the number of moles, and then the constant R will take that into account. T is the temperature in Celsius, which if we increase temperature, pressure increases as well. And V is the volume of the enclosed container in, it should say, cubic meters. So suppose we want to understand the rate at which pressure changes as we heat up some sample of gas in an airtight glass container. We're going to use the chain rule to get an expression for dp dt, which again is the rate of change of pressure with respect to the temperature increase. And we're going to break this down into the following 4 parts. If you want to get started on this and pause the video now, I encourage you to try at least parts A, B, and C before writing out the final expression for dp dt using the information in part D. And I'm going to switch over and work out parts of this with you. So the first part is apply the chain rule to get an expression for that rate of change, dp dt. And in this case, we see that it's written explicitly for us in the statement of the problem. P is a function of n, t, and v. And notice that r is an extra symbol there, but r is a constant. We're immediately told that r is not a variable, so we don't have to worry about rates of change of r. However, p is a multivariable function that has 3 input variables, n, t, and v. So we can express the rate of change dp dt as a combination or a sum of the different terms for each of those input variables. First, we have the partial of p with respect to n times dn dt. Then we have the partial of p with respect to t times dt dt. We'll get back to that in a moment. And the partial of p with respect to v times dv dt. And these are the 3 terms we need to consider. First of all, n is the number of molecules of gas. And if we lock up our airtight glass container and start heating it up, then the number of particles of gas, the number of molecules in this case, isn't changing. So in fact, no matter what we do to the temperature of this sample of gas, the amount of material in the container is not changing. There is no change to the number of molecules in the container. Okay, and let's just think ahead. This is really nice because this term will be 0. So the entire first expression of our 3 things that add up will just be 0 when we try to compute in part D. This is pretty typical if you have some expression with a bunch of variables. Some of them won't depend on each other at all, or we can say that they're independent of each other. So the number of molecules of gas in this case is independent of what we're doing to the temperature. So that will wipe out in the chain rule, and we'll be left with just some relation between the other variables. On the other hand, what's dt dt? Well, if you had to guess, and I just put this in front of you and said compute this, you'd probably say, well, the numerator and denominator cancel out, so we're left with 1, which is true in this case. But let's think about what this actually means. It's not good enough to say this is a, dt is a differential. It means a rate of change. And you should think of this as an instantaneous rate of change. So it's not really a number in the numerator or the denominator. However, this is a rate of change. So can we express t as a function of t and then take its derivative to get the rate of change? Well, t is just equal to itself. This seems really silly, but if we take the derivative of this formula with respect to t, then we just get the value 1. That's sort of a silly, but also mathematically consistent way of assigning a value to the symbol dt over dt. Another way to think about it, just as a rate of change, is how does an increase in the t variable influence the t variable? Well, 1 increase in t is the same as 1 increase in t. So this ratio is equal to 1. And we'll be able to plug those things and simplify a little bit. So in part D, we're told a specific rate of change of the volume with respect to temperature, namely that the volume is going to increase, and it'll increase proportionally to how much volume we start with. This is actually a differential equation that corresponds to an exponential function, but we don't need that much information to do this problem. So dv dt, the rate of change, is just given by this constant, 5.9 times 10 to the negative 6, times whatever volume we currently have in the container. And this is the volume of gas. So if we had a container that is made of glass, the volume would be taken up by the gas immediately, and the pressure would then change accordingly. But if we had a volume that was allowed to expand or contract, then that would be a different situation. So dv dt is given by this formula. Let's work out the original dp dt rate of change that we were asked about. And I just wanted to remind you that p is a function nRT over v, so that when we compute certain partial derivatives, we have this in front of us. So whatever dp or partial p with respect to n is, I know that this expression is 0. So the entire first term is 0, and I really don't care about computing the extra partial derivative if I don't have to. On the other hand, the partial of p with respect to t is something we can compute. If n, r, and v are all held constant and t is the variable, then this is a constant times t. So the derivative is n r over v. And we said that plugging in or evaluating the symbol dt over dt should be 1. Next, the partial of p with respect to v is a little more complicated. Let's isolate our variable v. Then the numerator is just a constant. So this looks like some constant times 1 over v, or v to the negative 1. And by the power rule, we can bring down that -1 and raise v to the -2. And if I rewrite that carefully, that will look like a denominator of v squared and then the same constant in the numerator. We need to multiply this by dv dt, which here is given by the expression in part d, which is written this way. Let's simplify this a little bit and we can talk about our conclusion here. So I noticed that my v and v squared in the second term here will cancel out. So I'll just have a v in both denominators, and I actually have an nr in both numerators. So I'm going to immediately factor out nr over v, and let's see what's left behind. In the first term, and I'm getting rid of the 0 completely. In the first term, I have a 1. In the second term, nr over v is taken out, so I have a t times this constant. So I'll write it as 5.9 times 10 to the -6 times t. So what this says is that the rate of change of p with respect to t still depends on the current values for n, r, and v, but because those are fixed values at an instant in t, this is really just a function of t. So this is a single variable function if we knew expressions for each of these, which we don't know off the top of our heads, but you can imagine plugging in the current values for those, and then just seeing that changes in temperature affect p, as this formula shows. All right, let's keep going. We've got a couple more problems to work through to practice with. And just like we can do in single variable calculus, we may not have all of the information available to evaluate the individual functions. P, in this case, the 3 input variables, p, q, and r, are further functions of some input variable x. We may not have actual expressions for those separate coordinate functions in terms of x, just like we may not have information about the inside of a composition of functions from single variable calculus, but nevertheless, the the chain rule in single or in multivariable calculus, together with some partial information about those constituent functions, can help us work out rates of change of the larger function in the situation. So here, let's suppose we have g as a function of 3 variables p, q, and r, given by this formula. And p, q, and r are all differentiable functions of a separate variable x, which have the following values that we can measure. And we're asked to compute dg dx, the rate of change of that parent function g with respect to that input variable x, when x is set equal to 2. This is another one that you can pause the video and work out on your own if you like. There's a whole table full of values to plug into the chain rule formula. And if you want to do so, pause the video now and work it out. I'm going to show you the chain rule for this expression g as a function of one input variable x, and it's given by, as we now come to expect with the chain rule for multivariable functions, 3 different terms because there are 3 input variables p, q, and r. We have the p term, which is the rate of change of g with respect to p times the rate of p with respect to x, and then similar expressions for q and for r. In order to work out parts of this formula, we're going to need an expression for the partial of g with respect to p, with respect to q, and with respect to r. And at the end of the day, oh, you see there's an answer at the bottom, so don't look too closely if you don't want the answer spoiled. We'll also need an expression for each of the single variable rates of change, but we'll get those from the table. So let's start by computing the partial derivatives that we'll need. The partial of g with respect to p, first of all, I see that there's a p squared in the exponent, and that's it. So r is a constant, q is a constant. And if we do the chain rule for the exponential expression, we will get 2p q times that extra r times e raised to the p squared q. And actually, right now, I'm going to plug in x equals 2 and evaluate each of p, q, and r in this column of the table. So these are the values that we're going to use. So at x equals 2, p is equal to 5. So I'll have 2 times 5. Q is equal to -2. R is equal to 7. And then e to the, we're going to have a lot of e to the p squared q. So let's just work out what that whole expression is. p squared, I said p was 5, so that's going to be a 25, and then q was -2. So the exponent every time will be -50. Just keep that one in your back pocket. Let's simplify this a little bit. We have, let's see, 2 times 2 times 5, that's going to be 20, or -20 in this case, times 7, that's going to be -140, times e to the -50. And keep in mind that e to the p squared q, when we plug in x equals 2, will always be e to the -50. All right, let's keep cranking. So the partial derivative of g with respect to q, I need that g formula again. Now q is the variable. It only shows up in the exponent of e. And r and p squared are both constants. So we will get the chain rule derivative again says that p squared comes out times the r downstairs, e raised to the p squared q. Here, p squared, well, p at x equals 2 is 5, so that's going to give us 25. R is 7, and then e to the -50, same exponent as we have. We'll have this the whole way through. We can simplify a little bit. Let's see, 25 times 7, it's only one less 25 than 25 times 8, which is 200. So this is 175 times the exponential expression. And finally, the partial of g with respect to r. This one's a little easier. This is r times a constant, since e raised to p squared q is a constant with respect to r. So that's a constant times r. The derivative will just be that constant, e to the p squared q. And again, we're going to plug in x equals 2 to give us e to the -50 for that whole expression. So I don't need anything up in the table anymore. Well, actually, sorry, we'll need things from the table. I'll need the rates of change for p, q, and r respectively. So our dg dx expression, we can start expanding as follows. I'm just going to read through this formula and plug each term in. So dg, or partial g, partial p, was our -140 e to the -50 expression. And the derivative of p with respect to x, when we plug in x equals 2, is right here on the table. That's 3. Next, we'll have the partial of g with respect to q. That was our 175 expression. And the derivative of q with respect to x at x equals 2 is right here on the table. So that's going to give us a 2. And finally, the r expression is, we have the rate of change, just e to the -50 for the rate of change of g with respect to r. And then the derivative of r at x equals 2 is -1. That's the last bit in that column on the table. Good, so this is the expression we have. You simplify, factor out an e to the -50, you'll get a term of -71. And if you get a decimal approximation, it's something like -1.3694. You don't really have an interpretation in this problem since we don't know what all of the variables represent. But this is an explicit computation of the rate of change of that function of g, that function g, as a function of the original input variable x, which influences all of the other variables. And that rate of change is this negative number. So g is decreasing when x equals 2. All right. So I promised at the start of the video that we would learn a trick for doing implicit differentiation in single variable calculus, but now using partial derivatives and a little bit of magic from multivariable calculus. So here's the problem that we're going to test this out on. We need to do a little bit of exploration before we solve the problem. So let's suppose that if we have, and forget about the first part with implicit functions for a moment, just suppose that we have the graph of a function given by the implicit formula x cubed plus y squared minus 4xy equals 0. Now, returning to this recall statement, on one hand, we can think of this as an implicit expression where y depends on x, but also x depends on y, and we weren't successfully able to solve for y as a function of x. But we can still compute rates of change using implicit differentiation from Calc 1. On the other hand, we could also think of the left side of this equation as a multivariable function. And in a moment, I'll write this as capital F of xy equals this expression in terms of the two input variables x and y. And we've taken a level curve of that function and set it equal to 0. So we took the height 0, or the z equals 0 slice of that multivariable function capital F. Can we use our knowledge of multivariable calculus of this function to determine the rate of change of y with respect to x at the point 3, 3? let's give it a shot. And the real utility of this approach that we're about to develop, by the way, is if we have more numbers of variables, and we can't just use our familiar approach from single variable calculus necessarily. This is going to be a trick that works in much broader generality. So as promised, let's let the left side of this implicit equation be some multivariable function capital F. And let's just use the chain rule to understand the rate of change of that function with respect to, in this case, x. We're trying to compute a rate of change of something with respect to x. So let's just write out what the chain rule says. Well, the chain rule says that we should take the x and y terms separately. The partial of f with respect to x times the rate of change of x with respect to itself. We'll come back to that in a moment. Plus the partial of f with respect to y times the rate of change of y with respect to x. And, you know, ding, 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 ding. This is what we're looking for. So at least the thing that we're trying to solve for appears in this equation. Now, you might say the thing that we're trying to solve for appears in the implicit differentiation equation that we would do in single variable calculus, and then you just have to solve for it. And I agree. But in this case, we're going to solve for this symbolically in a way that actually gives a formula for dy dx, no matter what function we used here, and then we'll apply it in this situation. So if I plug in, I'm actually going to simplify the notation a little bit and use f sub x and f sub y. But if I plug in what dx is, remember that that's the rate of change of x with respect to itself. That's just 1. Then I can simplify the whole expression to read as follows. So the rate of change of f with respect to x is given by the partial of f with respect to x plus the partial of f with respect to y times dy dx. And if we set the function f equal to 0 to get our level curve describing the graph in the statement of the problem, then, well, then 0 is equal to df dx. And we just said that that was equal to fx plus fy dy dx. And accordingly, we can solve for dy dx, the thing that we're after, write it as a function of the two partial derivatives of capital F. And this is really the innovation that we weren't able to use in single variable calculus when we didn't know about partial derivatives. So the expression will read negative fx over fy. I'm going to put this in a big box. This is a really useful formula for computing implicit differentiation and solving for the rate of change dy dx directly without having to do some sort of big, nasty algebraic mess, provided that you can solve for the partial derivatives of capital F, which we know how to do at this point. Let's apply this to the function in question, which was x cubed plus y squared minus 4xy. And in order to find dy dx, now all we need to do is figure out the numerator and denominator, which are the two partial derivatives of capital F. For the derivative with respect to x, we hold y constant, and we have 3x squared minus 4y. For the derivative with respect to y, we have x is constant, so we have 2y minus 4x. So ultimately, the rate of change of y with respect to x is negative fx, and multiplying by -1 just reverses the order of subtraction here. So I'll write it this way. Divided by 2y minus 4x. And I believe at the point, I think it was xy equals 3, 3, we can explicitly work out what the rate of change is. And really, geometrically, this is the slope of the tangent line to that implicit curve if we were to graph it. So at 3, 3 is, let's see, it's 12 minus 27 over 6 minus 12. And I'm going to cancel out 3's everywhere because I don't feel like doing too much mental math. This is, let's see, 4 minus 9 over 2 minus 4. That's a little simpler for me to think about. That's -5 over -2, or +5 halves. So the rate of change of y with respect to x at the point 3, 3 is +5 halves. Okay, we've got a little more work to discuss. I know this is a longer video, but I hope it's worth it because this is an extremely useful technique in lots of situations. By the way, here is a computer-generated graph of what just happened in the previous problem, we have this blue curve here, which is the graph of that implicit expression set equal to 0, which is secretly a level curve of some 2-dimensional or some 3-dimensional graph of capital F. And it's the height 0 piece. And at the point 3, 3, the slope dy dx at that point is given by the expression that we just determined. There's something important that I want to bring back into play on this slide, which if you're already reading ahead and ignoring me, you've figured out already, which is there's another vector that's perpendicular or orthogonal to that slope that we just determined, which is the gradient vector. We know that the gradient, among other things, is perpendicular to level curves of 2 variable functions and higher numbers of variables. So at the point 3, 3, the gradient vector sticks in a perpendicular direction to the slope that we just worked out. Keep in mind that the slope we just worked out was negative fx over fy. So it's negative change in x over change in y, where the changes are of that function f. And if you think about it, this is just the negative reciprocal of fy over fx, which is precisely the slope of, or the direction of the vector nabla f, that gradient vector. Why is that the case? Well, the components, the displacement components of the vector, the gradient vector of f, are the partial of f with respect to x, comma, the partial of f with respect to y. And the slope of the line that's traced out by that vector has the form rise over run. Well, the rise is the y component and the run is the x component, which ends up being partial f with respect to y over partial f with respect to x. That's exactly the perpendicular line, or the perpendicular direction to what the chain rule allowed us to compute. So we actually could have proven that previous problem using this approach, but we can do it by hand as well, just using the fact that this is an implicit expression that we can take partial derivatives of. So here's another applied situation. We don't have too much information here, but you can imagine assigning a little more information and assigning some values to some of the variables here to get an actual real-world problem to approach. So let's suppose a firm chooses how much quantity of some product to produce, but their profit, here we're going to write it pi of q comma alpha. This is the capital pi symbol in the Greek alphabet. Depends on the quantity q, but also some other parameter alpha that's outside their control. And maybe alpha is some tax, maybe it's some cost that's built into producing this type of product, or some regulatory function that's required to operate their factory. And the firm, once it knows the value of this alpha that they can't control, will then choose q that maximizes profit. So the profit, capital pi, depends on q and alpha, but this is saying that the alpha that they cannot control also influences the value q that they can control. They choose the amount, or the quantity q to produce. And we want to ask, how will their profit change as alpha changes? Explicitly, what is the rate of change of pi with respect to alpha? We can use the chain rule to evaluate this, and let's do so. So the chain rule for the pi function says that d pi d alpha, there's a lot of Greek letters here, but just go with me. D pi d alpha, the rate of change of profit with respect to that parameter alpha, is given by the chain rule, the partial of pi with respect to q times dq d alpha, however q changes according to alpha, and partial pi with respect to alpha times d alpha d alpha. And we have two things that we can work out here. First of all, we know that d alpha with respect to itself is 1. We've seen this happen a few times already. On the other hand, there's something clever hidden in the statement of this problem that really allows us to hack away some of the extra notation here, which is the firm in this case is choosing q after they know what alpha is in order to maximize profit. So if we choose q to maximize the profit, then any small changes in q in either direction, increasing or decreasing the quantity of production, would have a lower profit number. And that means geometrically that the slope of the tangent line in the change in q direction, that's the partial derivative with respect to q of the profit function, would have to would have to be 0. This is a maximum in the q direction. So that wipes out 2 terms here. And we can simplify our expression for the rate of change of profit with respect to alpha as the partial of profit with respect to alpha. This sounds silly, but what's really going on here is that when we choose some parameter to maximize our function, then the only thing that matters for a rate of change of the profit function is that parameter alpha. Another way to say this is Q is a separate calculation, but if we choose it according to the rule that it has to maximize, then alpha is really the only thing that directly influences profit. So there's not much more to say there, but if you chose some actual values here, you could quickly deduce things about the situation just using this insight that we just developed. So I'm going to wrap things up soon. And here's a graph of what's potentially going on in the previous example, which is if we choose our Q variable that is supposed to optimize the total profit, you can see that in the so profit here appears to be the height, and then alpha is just occurring in the alpha direction. If we were to zoom out and look at the third dimension, which is the Q direction, we would have to have a maximum, which says that as we change Q and alpha is changing Q as a result, the slope of the tangent line or the rate of change of the profit function only depends on how we move in the alpha direction. So it's really equal to the partial derivative in that direction. So here's the d pi d alpha in 2 variables, and here's the three variable partial derivative version, and those are the same slope. To summarize, and there's a lot of content in this lecture, but it all comes down to how do we visualize rates of change? For example, how can we visualize a function f of 2 variables x and y when each of those input variables are separate functions of another variable t? Can you explain why df dt, the result of computing that rate of change, cannot be interpreted as a slope of f over the xy plane? What is the difference between the symbols dz dx and partial z partial x? And how are these computed? And finally, how do you use the chain rule to differentiate an implicit expression from single variable calculus or with more numbers of variables? That's it for this lecture. Thanks for tuning in, and I will see you next time.